Hi, James.
Hi guys, how's it going?
Hello. It's been a while. Nice to see you again.
Oh yeah, a couple of years, isn't it?
Yeah. I need to say one conclusion from the previous talk from my side was that Tomasz weekend code looks way better than my production one. So I'm quite offended right now. I need to do some learning, but I think we all will learn a lot of cool stuff because James did amazing stuff with bringing to life is Wolfenstein 3D and F sharp. And I'm really looking forward because this one is, I would say, pretty famous in our community. And finally, we will see it alive. So thanks a lot. Thanks again, James, for coming here and show us the
Okay,
magic.
great. Just need to get my slides going. There we go. Great. I'll get cracking because this is a quite a lot to squeeze into 30 minutes, so it'll be quite high level. But people can always contact me in one of those places if they have any questions or want to talk about the code or how these things work. I'm always happy to talk later. I should just add quickly, these days, I think last time we spoke, I was working as a freelancer. These days, I'm CTO for a small company called Black Dot, and we develop open source intelligence solutions for tackling financial crime and things like that. It's a .NET shop predominantly. So that's what I get up to these days when I'm not kind of having fun with things like this. So it's not a lot, 30 minutes isn't a lot of time to talk about this. So I've kind of put the presentation in order of interestingness. And the code, which we'll eventually get to by a couple of steps, can all be found at the link you can see there. So without in mind, we'll get going. So Wolfenstein 3D, I think everybody knows about Wolfenstein 3D. I think when it came out, I was 16 or 17 years old, something like that. It was in 1992. And I remember when I first played it, running around the house, shouting and screaming that this changed everything to all my family, none of whom cared. I thought it was utterly amazing. It was so fast, and you were shooting Nazis. It was fantastic. It was mind blowing. I had a go at the time at writing a Raycaster in C, so I was kind of already deep into code at that point. But it was like really slow. Like it barely worked. It had weird fisheye effect going on, holes in textures, and I think it ran at like 1 frame a second, if that. And then one day I think it was 2022, I kind of woke up and I just, for some reason, and I don't know why, I thought I have to have a go at this again. I want to get a Raycaster working. And I kind of picked up F# as my tool of choice and got going. So real quickly, I'll give you a quick demonstration of it. You can find it online at the link you can see on the screen there, or you can download the code and just npm start it. But hopefully, if I can just move to my screen. So I'm just trying to move to my shared screen. Thank you. There we go. This is the game, and we get the pads out of the way. You can see it's Wolfenstein. Shoot some bad guys, and sort of all the kind of first level of Wolfenstein. Not all the sound effects are in there, but it all works. And there we go. So that's the kind of Wolfenstein game. That's all written in F#. It's using Fable to do the F# stuff, and there's a desktop version 2 running in .NET. If I could just switch back to my slides, I think I'm being an idiot and not quite sure how to do this, but somebody's helping me. Fantastic. So before we get into it, some important principles. Wolfenstein 3D is actually a 2D game with a really smart rendering trick. There's nothing 3D about it at all. So when you look at the kind of maths involved, it's all 2D. It's also really strictly grid-based, which I hadn't realized from playing the game. I knew it was grid-based because the map was a grid, but how the enemies move is grid-based too. So it's really strictly grid-based. And if you read anything about the history of the game, the ID guys, I love listening to John Romero speak. He's really interesting. They use their sort of Commander Keen 2D level editor to do the Wolfenstein maps to begin with. So it's really is a 2D game. The original game is written in C, and the source is really quite readable. It's really impressive. It's available on GitHub, like most of the ID software source. It's really worth reading. It's really interesting. When I thought about approaching a project, it wasn't really planned as such. I just thought I'll get it going. I'll have a go at Raycaster. I'll add some textures. I'll try and get the assets loading and kind of see where I get to. Halfway through, I thought, it'd be fun to get this browser thing also running in a .NET application on my desktop, just to see what that was like. And at some point in the journey of this, I looked at the original source code, but not right at the beginning. I kind of set off just looking at the game and trying to figure it out and reading. There's lots of things about Raycasters on the web you can find, and a few engines in various languages. So I was looking at those things and just trying to figure it all out. So how does Wolfenstein work? It's what we call a Raycaster. A Raycaster isn't a ray tracer. A Raycaster doesn't deal with any kind of bouncing of light or anything beyond an initial collision. Essentially, what it does is for each column on the viewport. So you've got you're looking at your rectangle, which we were looking at there when we showed the game. On the left, you've got column 0. On the right, you've got let's say column 320. And people who were around back then will probably know why I say 320. It was a width of the screen mode that was used for Wolfenstein and the Portal. You kind of walk your way across those columns, and for each of those columns, you cast a ray from the player's position, and you're looking for an intersection of a wall. And walls are not defined as vectors as you might expect. If you deal with modern kind of games, they're literally like cells on a grid. So if you look in the diagram I've got on the screen now, that's the initial room that you started in Wolfenstein, and each of those little squares I've shown is a cell on a grid, and what you're looking for is hitting a solid cell for each of those columns. So cast the rays out each column 320 times or n times, and look for a collision with a wall. How do you cast a ray? Well, a naive implementation is to kind of, which is possibly what I did back in sort of 92, 93 when I tried this. I really can't remember. Is you could kind of take tiny steps along a ray, along the vector of the ray, and look for a collision. The problem is you might, as that diagram shows, skip over. If your steps aren't really small, you can skip over. You can miss a collision, which might explain why I had holes in some of my stuff. You could take increasingly small steps, like infinitesimally small steps, but then the cost of doing that would be astronomical. And Wolfenstein ran on a 386, which is utterly puny compared to what we have now. So that doesn't really work. But what you can do is take advantage, and this is in the ID software. John Carmack was a genius. It really is clever. You can take advantage of the map being grid-based to step from cell to cell looking for the collision. So rather than look for a collision with a vector or make these tiny incremental steps along the ray, you can kind of walk the grid and think of a grid as drawing a line, a pixelated line, a low resolution line across your map. And that's what Wolfenstein does, and that's what the Raycaster I've implemented in F# does. And for me, it was I really struggled to conceptualize it at first, what was going on. But it was when I realized that actually I was drawing a low resolution line, it all suddenly started to make sense to me. I thought, oh, I get this now. Right, okay, this is a line drawing algorithm, and there's Bresnum, there's DDA. Wolfenstein uses DDA, which is what I've used here. But there's lots of ways you could do this, but it's not complicated. It's like, oh, this isn't that complicated. This makes sense to me now. That was a really kind of conceptual key for me. I would never have looked at the grid and thought, oh, I draw a low resolution line across this. Like that, I think that was a real big leap to get from one to the other and implement a Raycaster in 92. So DDA, you can I won't go into massive depth on this because of the kind of time limitations, but you can find lots about this online. Essentially, you calculate some initial values, and then you can kind of walk along using these values step by step to figure out where the next position is, when where the next grid cell is. So you're drawing the line. There's some pseudocode for it there. That's essentially what it does. You calculate the initial positions, and I won't read the pseudocode out, but I'll leave it there for a second. You essentially just walk along this line based on the kind of distance you want to travel, the two deltas, y and x. So along. Oh, I've now need to start walking up, and now I need to walk along. So it's kind of doing this staggered step thing. Yeah, and you can implement that pseudocode, which is exactly what I did for DDA. The other thing you need to be able to do, and this is the kind of another one of the rendering tricks, is when you hit a wall, you get the sense of perspective by calculating how high the wall is that you need to draw by how far away that wall is from the player. And you do that, what you do that, as I've shown in the diagram here. What you could do is do the actual kind of distance, the bird's eye distance, as it were. The Euclidean distance is the posh term for it. I'm not really a mathematician, so I don't really use terms like that. But the kind of direct distance from the player to the wall, you could use that. The problem with that is you get a fisheye effect, which is almost certainly the problem I had in 92. What you actually need to use is the perpendicular distance from the camera plane. So you calculate that distance, and that gives you the nice perspective, flat kind of view that you expect to see. I started this with a really simple implementation, which I'm going to quickly show. Just start this up and hope this works. So I had some problems earlier. Great, it's working. Phew. One sec. Could you guys swap me back to my screen, please? So this was my first stab at this, and we'll have a quick look at the code in a second. So it was just using colors rather than textures. On my screen, it's running really smoothly without the kind of streaming tech. You can see you can walk around this simple map I've defined. If you want to take a look at that, and this is kind of like the simplest Raycaster you could possibly build, there's a link in the slides to a project I put on GitHub called fsharpConf Raycaster. The code for it is really in game.fs. And at the start, I define a map. So this is the kind of grid-based map I've been talking about. And then there's some stuff to initialize the scene, so where the player is, what direction the camera is pointing in, the plane of the camera, which we need, things like the perpendicular distance. You can calculate the plane, or in this case, I preset it because I knew what it was. And then update frame just handles the controls. I'm really not going to worry about that. That's really basic vector math, nothing particularly interesting. But this render scene is the interesting stuff. So this is where the casting of array occurs. So I'm rendering all this to a 2D canvas, and just through HTML, the canvas element, and I get the context from it. And you can see here I start walking across the width of the canvas. So for each column of the canvas, I'm walking across it, and I need to figure out the position in the range of -1 to 1. So that's the next position. Calculate the direction of array as a vector. So for this column, and given where the player is, what's the direction of array to it? So that's the diagram we saw earlier. The current map position, and then we start the DDA process. So set up those initial values that were on the diagram, the step sizes, the initial distances, the deltas, and then I run a scan. So there's a lot of folding and scanning in this. It was a bit of and there's a lot of stuff to track along the way. And I must admit, this hurt my brain a little bit when I first came at this. It was quite difficult to kind of just get my head around because there's so much going on. But essentially, I'm applying the DDA algorithm in here, and you keep moving and you keep moving and you keep moving until you hit a wall. When you hit a wall, you then kind of bail out of this process. I'm also, just to note, tracking the side of a wall. So is it the north-south of a wall or the east-west of a wall? And that's tracked by 0 and 1 in here. When we get to the Wolfenstein game itself, it uses a DU to make it a little bit more readable. That's just so I can shade the wall slightly differently. So the light red and the dark red that we saw in the game, and the dark blue and the light blue you can see there, are not any kind of like complicated lighting effect. They're just, it's a north wall, so show a dark blue. It's a west wall, east-west wall, show a light blue. So it's quite basic. And Wolfenstein does that itself. Wolfenstein has light and dark textures for the walls, and it does exactly the same thing. So we'll see that later. When you found a hit, you then calculate this perpendicular wall distance, calculate the line height based on that, the height of the viewport, calculate where you're drawing from, and then I just draw a vertical line for that height centered in the screen. That stuff's in render.fs, and it's literally just, at this point, it's just wrappers over the context. That's just drawing a line of the context. There's nothing more complicated at the moment. So that's kind of like the most simple Raycaster you can do. If I could have my slides back, please. And the code can be found there. And I extracted this from my I found my kind of original Git repository for this and extracted this the other day. So that's kind of like the simplest Raycaster you can do on that link there. Adding textures is actually really simple. Once you've got this bit done, the Raycaster done, the other stuff is a lot more straightforward. If you think about the grid again, to draw a texture, you just need to figure out the texture's aligned to the cube. So each of those squares we had has a whole texture on it. The textures in Wolfenstein are 64 by 64 pixels, real high res stuff. They look great. I still think they look great, and the Doom ones look superb and very low res too. But they're 64 by 64, all of them. And all you need to do is figure out how far into the wall you are based on your hit, and then just scale the appropriate column from the texture. So it's really just kind of like scaling of an image. It's pretty simple. But when I came to do the texture mapping, I also wanted to go a bit more sort of original with it. I didn't want to use sort of high-level concepts in the canvas, so I started to use the byte array underneath the canvas, and it turns out, oops, have we gone too far? No, sorry. It turns out you can get hold of that. There's a method on there called get image data that returns you a JavaScript array buffer, which you can then use a data view or a typed array on top of Rava or a data view to manipulate. So this is the general render loop, and this loop is what gets you to full Wolfenstein, basically. You load the textures in the background. So I load those using images, just HTML images. Wait for them all to load, get the image data from them, and kind of conceptualize them in a texture. And then to do the output, I do the same. So I take the output canvas, which is the thing we're looking at. I get the image data at the beginning of the render. I then update that byte array as we go. So I copy the textures into it, column by column as appropriate. And then, it says begin render, but end render, I set the image data back in the canvas. So effectively in that loop, you're doing pixel manipulation, just as you would with the memory, the VGA adapter back in 92. I won't go into the code in this because of the time limitations, but there's the super simple implementation of this in that GitHub link there. All it really adds is texture loading and some this stuff around byte arrays and scaling the image, but it's not particularly complicated. We'll skip that because of time. And then we'll get on to the actual kind of Wolfenstein bit itself. By the time you get to the Wolfenstein game, you use a Raycaster in a couple of different ways beyond just the casting of the ray, which will come beyond just the rendering, which we'll come to in a minute. So in this, I've abstracted away the kind of Raycaster into some abstract just cast array and tell me what you've hit rather than combining it with a render as we saw in the previous code. I'm just going to find my Wolfenstein project and we'll start to take a look at this. Could you swap me back to my code, please? So there's a file. This is the actual Wolfenstein solution. Again, this is you would have seen the link a second ago. This is on GitHub. Some of the code isn't the prettiest because I was figuring all this out as I went. So it was quite interesting. But there's a file now called ray.fs that has an abstract function of cast, a function of cast in there that takes a few bits and pieces, set up some terminators, which we can see an example of in a minute. So how to start the thing off and when you want it to end. And this is the same code we saw before, but just it's been decoupled from the renderer and has a little bit more in here around understanding what the map looks like. So in the full Wolfenstein project, the map is a discriminated union. And there's essentially, you can see there's four different possibilities in the map. You could be a turning point, which we'll talk about in a second. You could be empty, self-explanatory. It could be a wall, it could be a door. Doors are quite complicated, and I'm not going to cover them here because they are quite complicated, and it would no way fit into this session. They involve like a half step because they very halfway along. Can I go back to my slides, please? Yeah, we'll skip that because of time. Render.fs. Sorry, game objects and enemies. So game objects and enemies are also, they're 2D as well. So there's no 3D models in it. They're just sprites again. You maintain them. You need to obviously draw them to get the depth perception right. You need to draw them in the right order. So they are basically sorted in depth order relative to the player. And then to clip them behind the wall. So imagine like a guard moving around a corner. You want them clipped behind the wall. As we cast the ray into each wall, we essentially capture the depth of that wall, which we know because we're doing those calculations we've seen already, and we use that combined with the depth of the enemy object to figure out, is there a wall in front of this enemy or this object. There's one other slight complication, and this really hurt my brain. Some of the sprites are orientable, so they have different, depending on how you're looking at them, they appear to the player in a different way. So a guard could be running away from you, moving sideways, diagonally. So each of these kind of orientable sprites, they have numerous frames of animations. So this is the running animation for a guard, but the running animation is then further broken down into the direction the guard is facing relative to the player. And you have to kind of figure out which of those sprites to show. So to do this again, I'm a particular visual person because it really hurt my brain. But essentially, to do this, I established 8 triangles around the enemy. So 8 kind of cones, and those triangles are all made up of vectors of one in terms of length, so a vector of unit 1 length. Each of those cones represents one of those sprites, one of those directional sprites, and then you calculate the directional vector between the player and the enemy sprite, and then scale that down to 0.5 units, so it'll fit inside one of these cones, no matter how far away the player is from the enemy. And then you treat that vector as a point, and you basically you figure out which of the triangles that point fits within. And again, it's right fascinating doing these things. I came across something called barycentric coordinates, which I've never come across before, which is a way of sort of describing triangles and triangular spaces, and you use that to detect, which triangle the point is in. So it's, didn't mean to go there. Sorry. And then the last thing we do is, as we draw those objects, we track if any of those objects overlap the middle of the viewport, which is then the weapon. So when you shoot, by the time you come to as somebody firing, you know which object is at the middle of the screen, if any. So if you could switch me back to my code, please, that'd be great. All the rendering code in the full Wolfenstein is in the file called render.fs, and there's just a few modules in here. So there's walls, which is the thing we were talking about earlier, but this is doing the actual Wolfenstein wall code, and this is the kind of returning of that data. So there's the Z indexes, which are kind of calculated. The depth indexes are calculated as we go. Then the objects. So you can see here, this is the code. This is the triangular code. So we have 8 quadrants to map 8 sprites. We figure out the size of a sprite in radians. So you just scroll along, there's a little degrees to radians thing on the end there. We calculate the player's relative position and we normalize it. That takes it to a length of 1. Then we calculate the vectors for the triangle. So we just loop across the kind of sprite quadrants, convert that to an array, and we're just looking to see if it's in here. Is this thing, which of these triangles, if any, is it in? And that gives you ultimately gives you the thing to render, and the right sprite to render. And then rendering is the same kind of code again. We're just literally drawing column by column for each game object, from the start of what we can see of them to the end of what we can see of them, and copying textures in. as we go. So setting pixels in this underlying buffer. So yeah, all the rendering code, if you're interested, is in here, is in this render.fs, which is the meat of it really. Can I go back to my slides, please? Weapon and status bar, they're pretty boring. It's just rendering images, nothing very interesting. Codes in render.fs. Bringing it all together, there's a file called scene.fs in the browser version, and it literally just pipes these things together. There's a little bit of setting of the graphics context to do and things like that, but it's all gets brought together there. Enemy AI, it's state-based, stationary patrolling, chasing. I mentioned turning points earlier. So when you see guards moving in Wolfenstein, they're following map points. So a cell can be a turning point, and that means the guard will turn in the direction of that point. So they just follow the grid, which is what I mean. Even the guard's movements are grid-based. They're not kind of moving on arbitrary vectors. They are moving across a grid. And in fact, if they don't move across a grid, things like turning points stop working, because if you don't hit one exactly in the middle, you can end up starting to deviate around and it goes a bit wrong. I said we use the Raycaster again. The Raycaster is always used to determine if a guard can see a player. If a guard can see a player, they might choose to shoot, and they might choose to break their patrolling and move from patrolling to chasing. So we reuse the Raycaster to do that. There's a file called ai.fs. All that code's in there, and I heavily referenced the original source. I do remember that for this because I wanted it to feel authentic, and it was difficult to divine from just watching the game what the AI was doing. And I think you can see from the source, I tried to keep this functional. The original C source code is not at all functional. It's C code. I did try it with the kind of Wolfenstein doing it in F# to keep things functional. I'm nearly out of time, so I'm not going to talk about these bits. Feel free to check the slides out later. Targeting the desktop was interesting. So that's thing I'll talk about. I hadn't thought about this when I started Wolfenstein. I wasn't planning this, so I ended up I use ImageSharp to represent the textures rather than the canvas and the HTML image element. I render the output using OpenGL. It doesn't mean I use the OpenGL 3D system. I render the output to a texture and then just stick the texture on the screen. So I think I use silk.net for that, which is various wrappers for Direct 3D and OpenGL and all those things. And I implemented some of the JavaScript things like data view and uint8 clamped array. I implemented some .NET versions of those, which were compatible with the signatures I was using, just to get that code running in the desktop. And the code's a little bit disorganized if you look at the solution file, because it really wasn't. I really didn't set off with that in mind, but it did show that you could get, you could multi-target. You could use Fable to target a JavaScript environment and .NET to target a .NET environment with the same sort of 80%, 90% same source code, and it would work, and it did work. And I was quite pleased and excited by that. I thought that was pretty cool, and it's something that's difficult to do elsewhere. Bunch of links to things, the code, some of the things I found helpful, and I'm out of time. So I skipped a few things there, and I guess I'm either out of time or maybe people have got questions for me. I shall hand back to the presenters.
Thank you very much. I'm really impressed by how people observe our strict and crazy time limits.
It's very hard. That was very hard.
I know. I've experienced it on the other side just a few minutes ago. Let me see if we've got any questions here. I don't think we do. Yeah, there's a couple of comments, but I think people are just excited about seeing Wolfenstein in F#.
It was pretty cool. I mean, I got a bit carried away with it. It took quite a bit of time.
Yeah, I can totally see how you sort of got distracted from real work for.
Yeah, I really did. Yeah.
Okay, well, thanks very much for showing this, and it was amazing to have it live. So thank you very much, James.
Thanks, everybody.